Well, good afternoon, everyone. It's the 11th of January, 2026. I am on Walter Bislin's channel, looking at the write-up on how they derive equations for atmospheric refractions. So on this page, he explains how terrestrial refraction is calculated from basic physical laws and how the equations and constraints used in refraction equations are derived. The same principle can be applied to derive astronomical refraction, although it's not the topic of this page. I'll circle back on that one. Atmospheric refraction is the bending of light due to a gradient of the refractive index caused by a density gradient of the air. Now, to be clear here, the bending of light is due to light leaving a medium of one refractive index value and entering into another medium with a different refractive index value. Now, the term gradient really tends to be misused by the people pushing this. And as far as the equations go, a gradient should be confined to the assumption that from a given point, and let's say it's the edge of space with a refractive index of 1.00000, descending down to the surface of the Earth, which has a refractive index of 1.003 approximately. There is a rate of change between the edge of space and the surface of our world. And if that is averaged out across that vertical height, you would establish a gradient. Okay, the gradient would be a grade or rate of change for the refractive index as it increases in density, getting closer to the surface. In a layer above the surface, refraction can vary considerably. Okay? If it varies considerably, it's not a gradient. Okay, it is called turbulence at that point. At any specific altitude, the IOR can change slightly up or down across that altitude. Without changing height, it can change considerably. Well above this layer, refraction varies only a little, and from that specific area, well above the surface, they can derive a mean standard value of rate of change. See refraction coefficient as a function of altitude. Let's toggle over to that to a minute. You have to realize that anytime you see little k, you are talking about a coefficient. This is a calculation based on two values which, if you come from a flat earth community, you would have to say the radius of the earth is an assumption by the globe community. Secondly, the radius of the curvature of the light ray. Okay, that's important too, because if light travels in a straight line, bends at an angle, and continues back in a path in a straight line, there's only going to be a specific path that the light can travel in order to continuously refract, and that is a light path that continuously progresses into a denser medium, not existing in a dense medium, not existing in a less dense medium. It is the change into a denser medium. At the point of change, or along the rate of change, refraction can happen. So when we say light slows down as it passes through a transparent medium, that is a deceptive statement. If light is moving in a vacuum, it will slow down when it enters into a transparent medium, at which point it will maintain the speed in that transparent medium of fixed index of refraction. This is not a braking force. The light goes from a certain speed to another speed. It doesn't continue to slow down unless it enters a denser medium. If it continues to enter a denser medium, it's going to continue to slow down. If it leaves that denser medium and enters into a less dense medium, it will speed up. So this is not a braking force that you can say light slows down in the medium, and as it slows down, it's going to continue to bend. That's very deceptive and incorrect. The index of refraction determines the speed of the light in the medium. That agrees with exactly what I just said. Okay, so again, as if once we get into, we might as well jump into it. Again, we've already just mentioned that little k here is a coefficient. And we're deriving equations. We're trying to relate k, a coefficient, to pressure and temperature and a rate of change. Okay, this is per meter of change. Per meter of change. In Kelvin or Celsius, we're calculating a rate of change. That is what this individual is doing. So, along the path that is being refracted, that rate has to change. The IOR has to change at a rate. Now, these charts are from data from Edwards Air Force Base. You know, you've got a balloon that they launch up 5,000 meters from the ground, and we can see how the temperature warms as it nears the surface and then switches back. There's heat that radiates to a certain height. The surface can be cooler. These are the readings on January 3rd, 2018. And from the temperature, humidity, and pressure readings, these can be applied into the Sidor equations to generate a value for index of optical refraction. Again, this shows the conversion in the end after, if this information has been put in properly, this would be the change in index of refraction. And there's really no sense in arguing the change in index of refraction. We know space is 1, and the surface again was 1.0003. But the rate of change happens for light that is moving downward through the altitude. Okay? We're moving downward through our atmosphere. And the rate of change, or the change itself, is what would create the first bend and every subsequent bend along that rate of change. Now, I took and brought in a standard screenshot of Snell's law. The people who are going to jump up and down say, well, our atmosphere doesn't have a solid interface, so Snell's law does not apply. Well, no, Snell's law is refraction. And, all of the all the principles in explaining refraction are the same. The only difference that you have an incident ray of light coming in, you have an interface. You have an incident ray coming in, and instead of a solid interface, you have a rate of change. Okay, this would be the vertical gradient. This would be everything that was just explained in these charts here. So, along this rate of change, you have a continuously refracting path of light. Okay? Mathematically, this is represented as a radius of the light's path. The radius of light travel. Okay. Not a problem with that logic. But the light originally started off in a straight line, and at some point, if it exits the rate of change, it's going to continue in a straight line. So when little r, this is the radius of the light path, is represented as not being constrained by the duration of the time it spends in a gradient, or its relationship to the gradient. Light that is not experiencing a rate of change or any change in IOR is not refracting. Okay, this is important. And if we go back to the opening pages, where I said I was going to circle back to astronomical refraction. Which page was it on here? The only light that really meets the qualifications for the lapse rate, the vertical change over distance, all of the time, would be for astronomical refraction. The light for astronomical refraction is going to generate from a celestial, a star, planet, the sun. That's coming from a medium which has a refractive index value of 1. And it's going to reach the surface where someone is going to observe it at a value of 1.0003. So while this individual claims to be deriving equations for terrestrial refraction, all of the methods of calculating are contingent on light that is moving downward through the vertical gradient, the gradient, and again, getting back to some other things that we just read here. if the density is not isotropic in a medium like air, light gets bent in arcs. That's deceptive. Light does not, isotropic does not mean it's a gradient. Isotropic, it's up or down, it's just not uniform. Okay, if it's not isotropic, the amount of refraction, the bending of light depends on refractivity gradient or lack thereof. Okay, it's not that if it's not isotropic, it's a gradient. If it's not isotropic, it can be a turbulent atmosphere. So this individual is really fixed on selling the refractive coefficient K, because they're trying to sell the concept of the curved path of light. The curved path of light is hidden in K. Let's read a little bit more here. We know that the bending of light does not depend on the magnitude of the index of refraction, but the index of refraction gradient. Again, yes, the gradient, the orientation, the rate of change. Okay, this is what determines the refraction, how progressively it's going to happen or not happen. Each blue dot represents refractivity gradient and refraction coefficients for a certain day. Well, this seems to be all over the place, which means it doesn't seem to be standard. At least to 200 meters. It's all over the place. So to create a standard, and it's really even not a standard, it is a footstone into selling, again, refraction as being a curved path of light, which it is not. Not in every occasion. It's a very specific occasion where it can be considered. A rate of change over distance happening because it's vertical. Okay, that is why this document is titled Refraction Coefficient as a Function of Altitude, as a function of altitude change. Light moving and changing altitude as it comes from the celestial to the surface, the planet, star, sun, to the surface. We could say that high mountains or a descending path of light has a rate of change too, but nothing significant to the point where we can take and derive these equations. A lot of these equations that are derived also talk about a height above ground level. Okay, not a specific altitude above sea level, a height above ground level. So if you're standing on a mountain that's 7,000 feet, you're still 0 feet above ground level on the mountain you're standing. How the temperature radiates off that mountain, how the humidity is released from that mountain, is different than the altitude of pressure. Pressure is going to follow this curve, and it is what it is. That's pressure above and this is wrong, height above ground level. This should be height above sea level. Because pressure is not going to very excessively based on height above ground. It's more height above sea level. So what else do we know here? There's just a lot of nonsense where someone continues to sell the curvature of the light ray. First off, you have to justify that the medium and the path of light, does the path of light move into a denser medium, a consistent denser medium on its path of travel? If it's moving horizontal, it is not. That's not to say it's not going to experience a change. That's turbulence. Okay? The IOR can change up or down based on pockets of air, the medium, the exact condition of the medium along that horizontal path. So what all does this mean? When you're correcting for refraction, and you've made the assumption that your method of correcting for refraction is going to be based on a coefficient that assumes the curved path of light. Let's get right back to the beginning. Okay? Radius of the curvature of light, assumption. Radius of the Earth, another assumption. C, little c, I got to circle back to that one. But if c equals a coefficient based on a radius of the Earth, well, again, we have two assumptions through calculations of assumptions that come up with another coefficient. And as these coefficients pop up in all of the formulas that drive this program, if they're rejectable, as I am saying right here, there's legitimate reasons to reject coefficients being used across the board. I mean, they're obviously generated from data, specific data based on a vertical path, down through a changing atmosphere. All well and good. But there's nobody showing constraints within the program itself when they take a look at a horizontal observation. And when the linear aspect doesn't work, we see a straight line, either over a globe or over a flat surface. And when it does not meet the expectations of either model, both parties are going to say refraction is at play. From the flat earth community, I believe that refraction causes a bend in the light, which prevents the light from reaching the observer in linear fashion, therefore causing visual discontinuity or apparent obstruction of what you would expect to see. And that is a logical thought process. The globe community, on the same horizontal, is going to say that there exists a medium that has a continuously increasing index of optical refraction in order to allow that light to continuously arc to follow their curved globe. Logically, our atmosphere isn't structured that way. Okay? It's structured vertically. Everything's vertical. Horizontal, all of these are the same. Or, in the sounding data, they vary wildly. This is all turbulence at a height, at an elevation. It does not have to maintain a consistent curve, a consistent gradient. The gradient that is being sold right here is a rate of change for light that is moving down through this path. It is not applicable for paths of light that are moving across, or paths of light that are moving at a much shallower angle, or paths of light that are moving up towards an observer that's higher than its origination point. So, yeah, I can legitimately reject this work. It's great that someone put time into it, but they didn't put into it a logical thought process. Okay, they were set on selling a radius curvature of a light ray. Again, the laws. Light travels in a straight line. Well, not according to this program. Light is always going to have the potential to have a radius. When you actually put this into Walter Bislin's program, and let's go there real quick. Let's go to the Earth Curve Calculator. Let's bring this up. Let's select a couple of things here. Feet and inches, of course. Let's do a comparison, globe versus flat Earth. Okay. Refraction is set at 0. 0 would be no refraction. Straight linear approach. Now, as far as the globe, they can take and adjust what they see on the targets in this program based on changing the curvature of the light ray. Okay? Why isn't there any refraction on a flat Earth? There is a spot in one of these where, while they're calculating this, and let's go back because I think I know where it's at. Come on. Yeah, they go into the apparent. Here we go. This is a note that someone brought up. This formula is independent of the shape of the Earth. Okay? Calculating the curvature of light is not dependent on the shape of the Earth. Refraction is not dependent on the shape of the Earth. But when you put it into a coefficient for formulas in an Earth curve calculating program, the formula is, contingent on there being a curve, supposed curve below it. And how they do it, if we know the apparent size of the Earth, and where's the apparent size? Refraction factor, apparent radius of the Earth. Many calculations for observations that involve the radius of the Earth, flat Earth observations, flat versus globe, like hidden height, distance to the horizon, assume a straight light ray. Okay. No, we don't assume a straight light ray all the time. We assume a straight light ray and light rays that can refract at an angle. Okay, we don't assume a radius ray. Okay, this is what this program does. It assumes a radius. So, but there is a trick. Oh yeah, it's a trick to keep the same equations for bent light. By increasing the radius of the Earth in the equations by a refraction factor and making the light ray straight, the geometry of the two situations is the same, but the narrative is completely different. Maybe the geometry works in order to get you where you want to go, but the narrative is wrong. And light doesn't travel on a curved path. You'd have to justify a medium that is progressively denser along that curved path that you would like to believe exists. And it doesn't. So there's just a lot of mathematical nonsense, word salad, talking things round and round, converting between gradients, and the people selling this slather conversations in gradient. Gradient this, gradient that. There's always a gradient. Qualify that the gradient meets the requirements for your curved path of light. Once you turn something into a coefficient, does not mean that that coefficient stands alone and can be applied anywhere. If what brought you to that coefficient doesn't exist how you're using it, it's being misapplied. It's being applied incorrectly. And nothing in Walter Bislin's calculator prevents you from sliding this bar one way or the other to give you a response in the model to that coefficient. What's really interesting here too, if this is the actual radius of the Earth, the 3959, the apparent radius right here, look at how it changes. All you're doing is you're doing the trick. You're changing the surface contour of the simulation model. And you're assuming that that's acceptable and a correct process of dealing with refraction, of compensating for refraction. You're not calculating for refraction at all. There's really nothing here that I'm seeing that is calculating refraction. You're calculating curved lines. Imagined curved lines. And what's interesting, like in Bobby Shafto's observations, is you can start ignoring things like the Saginaw, the bulge height, you get high enough off the ground and you assume an eye level, you're only trying to get away from the referent, the surface of the earth. You want to get up and away from it and, try to show your mathematical mumbo jumbo and start to ignore everything that you are observing that's at the water level. And the higher you get away from the referent, the more you can allow someone to assume their method of survey. The same people that are going to jump into this program and claim a curved path of light exists all the time. Well, except for when you're viewing a mountain. That's straight as an arrow. There's no refraction that can happen there. There's no refraction, again, as a function of height. Are we going back to here? Yeah, height. Height above the ground. Well, there may be 5,000 foot of elevational change between a guy standing on a beach and a guy at the top of the mountain. But he's still 0 feet above the ground level for the influences of our sun and the plants. Everything that heats up during the day and cools down at night. So none of this is relevant to terrestrial observations. Everything here is really should only be applied to astronomical observations. But that wasn't the intent of the individual who spent a lot of time trying to sell. Trying to sell a curved path of light and a coefficient unchallenged. And I am challenging it. I hope this makes things a little bit easier for people to understand what is happening here. You might want to watch it several times over to really get your head around what they're doing. These pages, anytime you type in, refraction coefficient as a function of altitude in Walter Bison's search, it's going to bring you to this page. You can take a look at his advanced curve calculator. A lot of these things, as they go through, they link you to the pages. Here, basic panel, refraction coefficient, challenged. I'm challenging it. Refraction angle. I'm sure that comes from a calculation based on the refraction coefficient. And I'm not denying refraction. Refraction is real. I'm not denying it at all. This program is, in my opinion, very dismissible as far as how it deals with refraction. And if you take the refraction module out of this program and you lock this thing down at 0, you are going to be more in line with the expectations of flat, purely geometric aspects, understanding where your horizon is, understanding the height of the bulge, understanding the drop beyond the curve. And both of these views here are going to be straight up orthographical, I would say. they don't factor in perspective. Things will get smaller with distance on both of them. It's oh yeah. I'm sure there's a lot more to it. I'm sure there's going to be flack from a community that's really just going to jump out and say nonsense or something else. Please point out, if you're going to make a comment, point to something specific of says, well, according to this is where you've got things wrong. According to the science, this is where you've got things wrong. And I may be wrong, or you may be applying your thought process wrong. Everybody's built a narrative based on something they feel supports the refraction narrative. But if you don't realize all the steps along the path of how these coefficients are derived, well, you may be misapplying the coefficient. It may be improper. And at that point, what evidence do you have? If you have to rely on changing an apparent radius of the Earth, I can tell you right now, there's a very, 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 very high probability that you're applying refraction incorrectly. Thanks for taking the time, and hope this helps.